Well, hello everybody. So we have been discussing distillation for so long, and in the last class, you were firstly we had given you introduction. After the introduction, then in the last class, the basic parameters and how to decide upon the pressure and other parameters, those things were discussed. Okay. So today we will first be going to discuss the theoretical number of stages, then the actual number of stages, and after the actual number of stages, this how to decide the optimum reflux ratio and so on and so forth. So, therefore, just a recapitulation, if you remember, it was told to you that the process design, in this case it is a equilibrium stage approach, where we decide that how close we are to the equilibrium, and based on the equilibrium and the operating line, we decide the number of stages. This is the traditional approach to find out the number of stages in contacting towers. So, therefore, we would find the number of theoretical stages in this particular session, the contact required for the desired extent of separation. How much separation we require, that depends definitely upon the feed flow rate, the composition, and also the distillate and the bottom compositions. And so, based on that, we would have to decide that what should be the separation that we want. And after the theoretical stages, after we have estimated the number of theoretical stages, then we would go for calculating the number of actual stages that we require in a tray column, or the packing depth that we require for packed columns. The actual depth or the actual number of stages, that would correspond to the separation that we have achieved with the estimated number of the theoretical stages of contact. Quite naturally, this is going to depend upon the efficiency of contacting. So, therefore, we will be discussing the efficiency, and then we are going to discuss, and finally, after that we would go for the sizing of the tower diameter and the tower height. So, therefore, as it was already mentioned, you need to know certain things, that certain things will be specified for you, and there will be certain other things which you have to decide in the course of the design in order to proceed. They will not be specified for your case. For example, the extent of separation, the feed conditions, they will be given to you. The composition of the feed definitely will be given to you. The distillate and the bottoms composition, that will also be specified, right. But you need to generate the equilibrium data. In order to find out the equilibrium data, you need to have information on the column pressure. Now, generally the column pressure, it is not specified. As a designer, you have to decide the column pressure. The basic considerations, they were already discussed in the last class, and it's quite evident that it was said, it was discussed both in the last and the last to last classes, that with increase in pressure, naturally separation becomes much more difficult, because the dew point curve and the bubble point curve, they come closer to each other. Then the reboiler and the condenser duties, they decrease, because the latent heat of vaporization is less. Quite naturally, if the dew point and the bubble point curves come closer, the condenser and reboiler duties become less. Then since at higher pressure there is a lower vapor density, and therefore, this column diameter is also less, and at the same time higher reboiler temperature and higher condenser temperatures are required with increase in pressure. And the lower limit, it is usually set up by the requirement if we require vacuum operations. And the other thing you already know, that in the condenser, the cooling, it is achieved either by cooling water or by air coolers, right. So, therefore, we would always like to operate the column under such a condition that the cooling water, which under Indian conditions, they are available, generally the inlet temperature is 33 degrees centigrade, the outlet temperature generally it is around 47 degrees centigrade. So, therefore, provided we have the pressure should be adjusted in such a way that we can use the cooling water in order to obtain the required cooling which is necessary for condensation in the condenser, right. And suppose that is not possible, under that condition we go for refrigeration, as we use refrigerant as a coolant in the condenser. Now, remember one thing, for both vacuum operations as well as for the use of refrigerants, definitely it adds to the capital and the operating cost. So, definitely we would not be preferring these things unless it is absolutely essential. It will be absolutely essential, suppose it happens that we would like to use either cooling water or maybe say air coolers, and we find that for using these particular things, and we have to go for a combination of high pressure operation and using of refrigerants. It can also happen that the top product that we get, that particular top product, the product, it decomposes or it deteriorates or it cracks at the temperature of the condensate. Under that condition, in order to reduce the temperature, we would prefer a vacuum operation. So, therefore, normally as an initial guess, what we would prefer to do is, we would like to keep the distillation pressure to as close as possible to ambient conditions, such that if we can use cooling water or air cooling in the condenser. So, if this is possible, that by keeping the distillation pressure close to the ambient, we can use cooling water or air cooling in the condenser, we would go to that particular pressure close to the atmospheric. For normal cases, normally we usually take a 1.1 or 1.2 kg per centimeter square, and we usually try to operate under that condition. Well, after that, so therefore, normally the column pressure gets fixed up in the way I have said. When I say column pressure, again you must be remembering this refers to the top pressure of the column. Okay. And usually if the pressure drop within the column is not very high, you do not know that in the beginning. So, in the beginning you assume the top pressure and to generate the VLE data at the column pressure or at the column top pressure. After the entire McCabe Thiele has been worked out, the actual number of stages has been computed. Under that condition, you can compute the bottom pressure, the bubble point of the bottoms product. Under that condition, you can again calculate alpha. If you find that the alpha top, it is close to the alpha bottom, you are fine, you can proceed. In case you find that there is a remarkable difference between alpha top and alpha bottom, under that condition you have to rework and generate the equilibrium data for a average alpha, which, as I have already mentioned, this is the geometric mean of the alpha top and the alpha bottom, right. The next thing is the condition of the feed at the column pressure. Now, if normally what happens, the feed, it is available as a liquid, and then what we would prefer to do is, we would like to heat it till at least the bubble point or till it becomes a two-phase mixture, and then we would like to introduce it in the column. The primary reason for doing this is that, the primary reason for doing this is that we would like to minimize the heat transfer or the interaction between the feed and the streams within the column, right, because in this interaction, if some amount of enrichment is lost, that is not going to be a desirable situation. So, therefore, we would like to have the feed either under the saturated liquid conditions, because under that condition what happens, the vapor flow rate below and above the feed flow rate, they tend to be equal, and that is not at all disturbed. The other thing for preferring a liquid feed is that what happens, you are going to pump the feed inside the column. Now, when you are going to pump the feed inside the column, then by this means also there is one way for increasing the column pressure. So, therefore, normally to start with, what we assume that the feed is under saturated liquid conditions. Well, the next thing is, so therefore, more or less the feed flow rate, the feed condition, the column pressure, everything has been done. The overhead condenser type, unless it is specifically mentioned that a partial condenser is required for some particular purposes, we will always go for a total condenser. And the reboiler type, we can select the reboiler type. And the important thing is, this is also one more thing that we are required to select. the reflux ratio with respect to the minimum reflux ratio, which I am going to discuss in the course of this lecture. And from this particular inputs, what are the outputs that we would expect? Definitely the bottom and the top products, this can be obtained from a mass balance equation. Then the number of equilibrium stages which we are going to get from the McCabe Thiele method. The minimum reflux ratio I will be discussing in due course. The boilerplate in the reboiler, and the condenser and reboiler heat loads, that also I will be discussing. Then after that, once the number of equilibrium stages are obtained, we can find out the actual number of stages, the feed stage location, and also the stage wise vapor and liquid composition. So, therefore, mainly what you have to decide on this is firstly the operating pressure, as I have already told you, the feed condition and the reflux ratio that you are going to work with. Now, regarding the reflux ratio, if we assume that the entire column is a standalone system and the cooling water and the steam, they are, we just assume that we do not get these things from any other part of the plant, then in that case what we generally the optimum reflux ratio, it is or rather the reflux ratio, it is selected based on the optimum design, and this optimum design, it is decided based on a trade off between the capital cost as well as the operating cost. Now, it is quite evident that suppose you start with a very low reflux ratio, extremely low, say almost we are not introducing any reflux at all, that is minimum reflux. What happens? Your separation, how the feed composition is fixed, how much amount of separation you have to achieve, you know. So, for that particular separation, if the reflux ratio is very less, then in that case naturally you would require an infinite number of trays in order to effect this separation. So, if you are requiring an infinite number of trays, naturally what happens? The column cost, that becomes infinite. Of course, under this condition, when you are not generating reflux, so for that particular condition, your condenser and reboiler heat loads, they are also much less. But the column cost is infinite because the number of trays that you require is infinite. Now, gradually you start increasing the reflux ratio. Whenever you start increasing the reflux ratio in order to effect this particular separation, you would require lesser number of trays. As a result, your column height will be decreasing. As a result, the capital cost, this is the capital cost. So, therefore, the capital cost will also be decreasing in this way. But at the same time, you have to remember that what happens, you are generating more and more reflux. In order to generate more and more reflux, the condenser heat duty has to increase. Quite naturally, the reboiler heat duty has to increase. When you are generating more amount of reflux, naturally the vapor liquid traffic in the column increases, the reboiled vapor amount increases, so naturally the vapor liquid traffic in the column increases, and definitely that calls for a larger column diameter. So, therefore, as you are increasing reflux, we find initially there is a decrease in the cost, primarily because the number of trays necessary for bringing about this separation, and as a result the column height, that starts decreasing. But along with that, since the column diameter and the reflux reboiler and condenser heat duties, they are increasing. So, therefore, this decrease occurs till a particular limit, and after that the capital cost starts increasing. On the other hand, if you consider the operating cost, and when you are increasing the reflux ratio, naturally more and more amount of reflux is generated. When more and more amount of reflux is generated, so naturally the heat duty in the condenser increases. When the heat duty in the condenser increases, the amount of coolant in the condenser increases, the cost of coolant in the condenser increases. When the more amount of reflux is introduced, there is also an increase in the amount of reboiled vapor. When the amount of reboiled vapor increases, quite naturally the heat energy which is added to the reboiler, that increases, and therefore, the reboiler heat duty also increases. So, therefore, we find that more or less the operating cost, this is the operating cost, it keeps on increasing with reflux ratio. So therefore, if we add the two, if for any particular reflux ratio, if we add the capital cost and if we add the operating cost, then we get the total cost of the column. So therefore, what do we find? We find that with increase in reflux ratio, the total cost of the column, this is usually expressed as the annualized total cost. You will come to know about what does an annualized total cost mean in the next class. So therefore, we find that the annualized total cost, this initially decreases, it comes to a minimum and then it increases. So therefore, over this particular range, if you find, we have the column can be operated at the minimum cost, and therefore, this corresponds to the optimum reflux ratio. So optimum reflux ratio, it is decided based on economics of the column. Well, so therefore, so what you have done, you have decided the column pressure based on which you have generated this particular equilibrium data. This is at the column top pressure. Next, what you have done, the feed condition, it is decided, right? And after that, you know the distillate composition, you know the bottoms composition. Now, generally for binary fractionation, we use a graphical procedure which is commonly known as the McCabe-Thiele procedure for binary fractionation, and this is constructed on this particular XY plot. Now, this McCabe-Thiele procedure, it is based on certain assumptions, due to which the constructions becomes much easier, and therefore, we can approach, or rather we can find out the total number of ideal stages by the graphical procedure. What are the assumptions? First thing is, we assume that both the components, they have nearly the same molar heat of vaporization. So therefore, whatever heat it is absorbed by the liquid in vaporizing, this is released by the vapor while it is condensing. Quite naturally, as a result of that, this particular procedure, it does not include the detailed thermal balances, and it also neglects the sensible heat changes, heat of mixing and heat loss from the column. So therefore, this particular procedure, it does not include energy balance, it just includes the mass balance, the overall mass balance as well as the component material balance. Just on these two, the entire process, it is based. The heat duties, they are just used in order to determine the condenser heat duty, which has been designated as QC, and the reboiler heat duty QR. Other than that, we do not use this, and we find out that for each particular R, there is a corresponding ideal number of stages which will be required for separating the feed of composition XF into a distillate composition of XD and a bottom product composition of XB. Well, so therefore, what we do initially, what we have done, we have constructed the equilibrium curve. After the equilibrium curve, we are required to construct the operating lines. What are these operating lines? These operating lines, they relate the liquid composition on any particular stage. So, suppose we take this as the nth stage. So, therefore, in this particular nth stage, what happens? The liquid which falls down. This liquid, it is designated as L and Xn. Now, let me tell you, since we assume equal molar counter flow. So, therefore, for a saturated liquid feed, the liquid molar flow rate in the enrichment section of the column is equal. The liquid molar flow rate in the stripping section of the column is equal. In the enrichment section, it is denoted by L. In the your bottom section, it is denoted by L bar. For a saturated feed, we know it is quite evident that L bar equals to L plus F. The vapor flow rate from this particular stage N, this is designated as V, and the composition, it is designated as Y n. in this case. Okay. So, therefore, the subscripts they denote the tray number from which the stream has been generated. This is number 1. Number 2, you have to remember that these columns, they usually the trays are numbered from the top. So, therefore, the top tray is 1, this next tray is 2, and in this particular way it proceeds towards the bottom, right. So, therefore, if we observe this particular part, then in that case what do we see? We find out that for any particular tray n, say in the enrichment section, we find that the liquid which is falling down, as I have said, that is n, the vapor the composition is x n. The vapor which is entering this tray n, naturally it is entering from the n plus 1th tray. V n plus 1 is definitely equals to V n. V n is the vapor which is leaving this particular tray n. The composition is y n plus 1, right. And here we know that this is d and the composition is x d. So, therefore, if we have a material balance around this particular part, so therefore, under that condition, what do we know? We know that here V is entering, L is coming down, from here D is coming out. So, therefore, if we make a material balance around this particular part, we can, the overall material balance gives us this, and the component balance it gives us L x n plus d x d equals to V y n, right. From here, V y n plus 1, right. Now, from here if you divide it and then you get L by d equals to R in that particular way, I will not be going into the details, plus x d, this becomes R plus 1 into y n plus 1, from where we get the equation of the operating line in the enrichment section operating line. We get this as y n plus 1 equals to R by R plus 1 x n plus x d by R plus 1. So, what does this show? It shows that the enrichment, if the reflux ratio is constant, then this is the slope of the enrichment line and this is the intercept of the enrichment line. And for x n equals to x d, what happens? You can very well understand y n plus 1 equals to x d. So, therefore, one point on this particular line that is going to lie on the, diagonal curve. So, therefore, this point, this corresponds to the point of x d x d. And the other thing, suppose now we consider the bottom section. For the bottom section, then in that case, in the same way, for the bottom section usually we denote the tray numbers with m, and in that particular case the liquid which will be falling into this bottom section, that is L bar. The vapor which is rising from the bottom section, that is V bar. The composition is say y m plus 1, this is x m, and here from here the thing which is coming out, that the flow rate is B and this is x b. So, therefore, for this particular case also, if we write down the material balance in a similar way, we would get L bar x m equals to V bar y m plus 1 plus B into x b, from where we find out that the stripping section operating line, the equation can be given as the L bar by L bar minus B x m minus B by L bar minus B into x b. Now, in this particular case also, if you put x m equals to x b, that means for the last tray where m corresponds to the last tray, if you put x m equals to x b, then in that case if you substitute it here, you will get y m plus 1 equals to x b. So, therefore, from here also we find that one particular point of the stripping section operating line, that should also lie under this particular condition. So, therefore, we have generated the enrichment section operating line, we have generated this enrichment section operating line, we find that it originates from this particular point, and the intercept under this condition it is x d by r plus 1. The stripping section operating line, we know it originates from x b, but we do not know about the slope or any other point. Definitely we know that this line is going to intersect the rectification section operating line under some particular condition, but depending upon the slope the intersection point can change. And quite naturally the point of intersection should correspond to that particular point where we will be changing from the enrichment to the stripping section, or in other words this particular point it should correspond to the feed point. Now, how to locate, rather how to fix up the stripping section operating line? For that we need one more line which is known as the feed line. Again, for the feed line, if you consider, say suppose this is the feed tray. So, therefore, on this particular tray F is the flow rate, ZF is the mole fraction, HF is the HF it is going to be the molar enthalpy, and the liquid which is falling on the feed tray it is L, HL, and the vapor which is rising from here, the vapor has V, HV, right, and this particular tray number it is NF. So, therefore, the vapor flow rate which is rising from this tray it will be NF, and the liquid which is falling to here it is going to be X NF minus 1, right. So, in this particular case also, just like I have done for the enrichment section and the stripping section, we can write down a overall material balance, and we can also write down a component material balance. For the overall material balance, what do we expect to get? For the overall material balance, quite naturally it is going to be F plus L plus V bar will naturally be equal to L plus V, right. F is entering from here and L it is falling from the top, and V is which V bar is rising from here, and then so we can write this down. From an enthalpy balance we can write F HF plus L HL plus V bar HV equals to L bar HL plus V HV. You will remember that we had assumed that the molar latent heat of heats they are the same, right. So, from there we get L bar minus L into HL, which is equal to V bar minus V into HV plus F HF, fine. So, from here we can find out that L bar minus L by F will be equal to HV minus HF by HV minus HL, and this particular ratio, this is known as the Q, it is known as the Q factor. This particular Q factor basically it is the heat which is required to convert 1 mole of the feed to the saturated conditions divided by the molar latent heat of vaporization, right. So, we can express this particular point, this particular parameter either by Q or maybe by the by F, where Q is the fraction of feed as liquid, F is the fraction of feed which is as vapor. So, naturally F plus Q becomes equal to 1. So, therefore, we can very well understand if you see that the heat required to convert 1 mole of feed to saturated vapor divided by the molar heat of vaporization. So, you can understand that depending upon the condition of the feed, the Q is going to change, right. For example, if we have liquid feed at its bubble point, we have Q equals to 1. If we have vapor feed at its dew point, so therefore, this corresponds to saturated liquid. If we have vapor feed at its dew point, under that condition quite naturally what we will be having Q equals to 0. So, therefore, this corresponds this corresponds to saturated vapor. If you have partially vaporized feed under that condition, what will you expect? For partially vaporized feed, quite naturally Q will be lying between 0 to 1, right. And suppose we have cold liquid feed, under that case what will you expect? Suppose the liquid feed, it is below its bubble point and the bubble point is shown by this, then in that case, in this case quite naturally it will be 1 plus the Cp of the liquid, the extent of subcooling which is there, divided by the lambda, right. And in the same way, if it is superheated vapor, then in that case it is going to be minus Cpv into Tf minus T dew point of the feed divided by lambda. So, therefore, depending upon the feed, you can understand that there are different situations. This corresponds to saturated vapor, this corresponds to saturated liquid, and then this corresponds to the two phase mixture. And if you have a feed Q line in the under this condition, it is superheated vapor, and this corresponds to subcooled liquid. In the same way, the way I was proceeding, in the same way if you proceed, you will get the equation of the feed line as well in this particular form, right. So, from here what do you know? That for the feed line, the equation, the slope is given by Q by Q minus 1, or in other words minus of this, in whatever way you write. So, depending upon the feed condition, you are in a position to find out the slope. And also you know, for this particular case, if your x equals to xf, then in that case your y also becomes equal to xf, of course, or rather if you put it at zf, then your y also becomes equal to zf. So, therefore, we find that for the feed point as well, this also there will be one point on the Q line which is going to lie on the diagonal line, right. So, therefore, you can locate the feed point and you can also find out the slope of the feed point. So, now what do you have? You can construct the upper operating line. One point you know corresponds to xd, and the intercept under this condition, that corresponds to xd by r plus 1. You can find out you can locate the Q point. We had started with saturated liquid, therefore, this is the Q line, it has originated from xf. Now, once you know this particular point, then in that case you know one point on the stripping section operating line as well. So, from here if you join, then in that case you have got the stripping section operating line as well. Moment you have got everything, now you know that at each particular stage what happens, since it is an ideal state. So, therefore, the streams which are leaving the ideal stage, quite naturally they will be lying on the equilibrium curve, and the operating line. So, therefore, the change in composition, this will be varying from the operating line to the equilibrium curve. So, therefore, in this particular way, if you start dropping the stairs, then in that case you would each particular step that you are generating, that corresponds to a single ideal stage. So, therefore, we start from this point which is xd, we start dropping the staircases. This particular staircase construction is made between the operating line of the enrichment section and the equilibrium curve. Simultaneously, we can also start from here, and we find that if we are dropping in this particular way, then at the point of intersection we change over from the enrichment section operating line to the stripping section operating line. So, in the enrichment section we find that the staircases are constructed between the enrichment section operating line and the equilibrium curve, and moment we cross this point of intersection, these steps are constructed between the stripping section operating line and the equilibrium curve, right. So, in this particular way we can construct the number of steps, and usually we find that we might not end up in an integral number of stages when we start from x d and end up in x b. Here itself you can find that we could not end up here. So, under that condition naturally a fractional stage is not possible. So, therefore, we round it off and we go to the next higher number of stages. In that way we complete it off. Now, there is one other thing. For when you are designing a new column, definitely what we would be doing, we would be having this particular crossover just at the point of intersection. But suppose we have started with an existing column. Now, in an existing column naturally the location of feed entry will depend upon the nozzle that is fitted with the column shell. We cannot make another nozzle just to introduce the feed. Now, for such a case, remember, feed can be introduced anywhere between this particular zone, right. Suppose the feed is introduced somewhere here. Under that condition, what we do, the steps they are drawn between the upper operating line and the equilibrium curve till this much, and after that we shift over and draw the steps between the lower operating line and the equilibrium curve. Also, we can introduce the feed under this condition. For such a case, we would be drawing the steps with the upper operating line and the equilibrium curve till this point, and then we will be shifting to the lower operating curve. For both these cases, you find that we have started with the same top and bottom composition, same condition of the feed, but in both cases we find what are the number of steps 1, 2, 3, 4, 5, 6. This case also it is 1, this is 2, this is 3, 4, 5, 6, almost 7. But if we make the crossover at the point of intersection, then definitely we find that throughout the entire range, the operating curve is furthest from the equilibrium curve, and as a result we will be having the minimum number of trays. So, therefore, we find that if really we would have we would want the minimum number of stages, then the crossover from the upper operating line to the lower operating line has to happen exactly at the point of intersection of the enrichment section operating line, the stripping section operating line, as well as the Q line. This is going to give us the best design. Now, along with that, we would what I would like to tell you is that the entire thing was discussed based on a particular reflux. Now, this particular reflux, it can vary between two limiting conditions. One limiting condition is the total reflux condition. Quite naturally, it is very evident that the entire liquid from the condenser is introduced into the column as reflux, and we are not drawing any product. What is the other extreme? The minimum reflux condition, where we almost do not introduce any particular reflux into the column, right. And the design reflux will always lie between these two limiting conditions. In the next class, we are going to discuss the concepts of total reflux, minimum reflux, and after that how we select the reflux ratio, and we will also be doing a problem just to discuss whatever we have been discussing, or rather just to demonstrate the process of finding out the total number of ideal stages. So, this much for today. Thank you very much.